1.3.8 using the correlation coefficient. So let's look closer at correlation coefficients. Putting the numbers in context, match the variables to the scatter plot you think they best fit. Be prepared to explain your reasoning. So let's take a look at these. First, let's look at the plots themselves. For A, we can see that there is a direct positive relationship. Okay, so the correlation coefficient is going to be, pretty good here. Okay, for the next one, we see that there might be some kind of loose association between the x and the y, a positive possibly. When we go down here for C, it doesn't look like there's any kind of correlation here. And for D, it looks like there may be some kind of negative correlation here, or negative slope. And the correlation coefficient might not be very good here because they're all over the place, right? These dots are all over. So let's see what we can figure out. For number one, daily low temperature in Celsius for Denver, Colorado, and boxes of cereal in stock at a grocery store in Miami, Florida. Okay, so right away we can see that there's probably no relationship here between these two here. We've got one in Denver, we've got one in Miami. So for that, I would probably think that it would be C. Okay, there's just really no correlation between those. For the average number of free throws shot in a season and the basketball team score per game. So for this one, it may be good to look at this for B. Okay, there is a loose correlation here. Okay, and if we kind of compare it to the other ones, we can probably, by process of elimination, choose B. Measured student height in feet, measured student height in inches. Okay, so our x variable, our y variable, is going to be a direct correlation between those, just because you're basically just converting one to another. Okay, and then average number of minutes spent in waiting room and hospital satisfaction rating. So, right, if you're waiting a really long time, you're probably not very happy about the, satisfaction rating is probably not very good. So we could go ahead and put D for that. There is a negative slope here. Okay, so for the next one, we've got 8.2, never know how far you'll go. Now, for this lesson here, Priya takes note of the distance the car drives and the time it takes to get to the destination for mini trips. Okay, so distance is x, travel time is y. Distance is one factor that influences the travel time of Priya car trip. What are some other factors? Okay, so let's go ahead and answer these, and then we'll talk about graphing this table. So one of the first things we could think about here are, what are some of the things that influence travel time? So traffic, stop signs, stop lights, refueling, whether the driver is in a hurry or not, driving on surface streets or interstate, weather conditions. Okay, those are all things that are probably going to influence the car trips, okay, how long they take. Which of these factors, including distance, most likely has the most consistent influence for all the car trips? And explain your reasoning. With this question, distance is going to be the most consistent influence, since it is always part of the reason a trip will take the time it does. So all the other factors are only a factor sometimes, right? So you might hit all the green lights, you might hit all the red lights on a certain day. Maybe the weather conditions are better on one day than the other, but the thing that's going to be consistent is going to be the distance. Okay, so we'll go ahead and put distance for that one. Now we're going to use technology to create a scatter plot of the data and add the best fit line to the graph. Okay, so there is a link to get to the table information, okay, that is in Illustrative Mathematics because you don't want to have to like type all of those data points, right, on the table. So what we can do is, here is the table. We can copy, right, all that information on the table. Oops. Okay, now it's not going to cooperate. Control C. Now we're going to go to our graphing calculator. And for this, we don't put the table in here. Okay, what we can do is we can just Control V. All right. If we put table, then what it's going to do is it's going to put the x values in y. Okay, sorry, it's going to be x2 and y2 when we paste it. So don't put the table in, just copy and paste right in here. Hopefully that makes sense. So when we do that, we're going to get this scatter plot. Okay, and so there's that part of the problem. Of the data, and add the best fit line to the graph. Okay, so let's go ahead and do that. So remember, when we're doing our best fit line, we're going to come down here and we can add a expression. Okay, oh, I guess I could have gotten rid of that. And let's get rid of that. And let's add an expression. So if we put this into slope-intercept form, we would have y equals mx plus b. Okay, and so here we can see that it is giving us an exclamation point. Too many variables. Try defining m or b. So what we're going to do, I'm going to go ahead and hit all here. So this isn't necessarily what we want. What we want is an approximation. Okay, it might give us the same, but I want to show you how to do this. So what we're going to do is we're going to put y1 and we're going to put x1. Okay, so now instead of that equals, we're going to put our little not equals. I can't remember what that's called. So now what we're given is the line of best fit right here. Okay, we're given our slope, we're given our y-intercept, okay, we're given our correlation coefficient. We can also plot our residuals as well. Okay, so what we have is that information. What do the slope and y-intercept for the line of best fit mean in this situation? Okay, so basically what is happening here? What does this information relate to us or relay to us? So the slope represents the number of minutes it takes to drive 1 additional mile using the linear model. Assuming the linear relationship continues, the y-intercept represents the number of minutes it takes to drive 0 miles. This may account for things like time getting ready or warming up the car before driving. So let's go back and take a look right here. So our y-intercept is 4.14. Okay, so that would be the time warming up the car or any of those other variables that we may have. And the slope is 0.93, okay, or 928, depending on how far we want to round. And so that is what gives us the slope, okay, the number of minutes it takes to drive 1 additional mile, okay, 1 additional mile. Okay, so let's take a look at the next one. Use technology to find the correlation coefficient for this data. Based on the value, how would you describe the strength of the linear relationship? So when we come back to our graph, we are going to come over here and we're going to look at the R value. So the R value is 0.99, okay, 0.99. So when we go back here, r equals 0.99. Since r is near 1, the linear model fits the data very well. Well, not very well, very well. So remember, if the correlation coefficient is 0, it does not fit it at all. If it fits it at -1, that's good. If it does it at +1, it's very good. Okay, so that's basically the information that you're going to need for that. How long do you think it would take Priya to make a trip of 90 miles if the linear relationship continues? If she drives 90 miles, do you think the prediction you made will be close to the actual value? Explain your reasoning. Okay, so let's go ahead and take a look at this one. So what we're going to want to do here is we have our y equals mx plus b. Okay, we're going to go and we're going to grab those m and b values again. So let's take a look real quick. So we have here our m, okay, and then we have our b. So I'm going to go ahead and put those values. I'm going to rewrite this as, y equals 0.93x plus 4.15. All right, so now what we're going to do is we're going to plug in, let's see, 90, okay? And so when we do that, let's go ahead and rewrite this. Y equals 0.93 times 90 plus 4.15. Okay, so let's go ahead and calculate that value. And this gives us y equals 87.85. All right, so remember that our correlation coefficient is really close to 1. So the data in our table right here, we can see that our best fit line is here, and the correlation coefficient is close to 1. So it's probably pretty true, okay, that this is going to continue along this path. Okay, if the correlation coefficient was different, we wouldn't be able to say this with as much certainty, but here we can say that it's probably going to continue on this line. And so when we go back and we look here at our data, okay, our information that we figured out, this is probably going to be a pretty good estimate of the trip, like how long, okay, it's going to take. Okay, let's go ahead and take a look at the next one here. So let's see, sorry about that. Let's go back here. So what I've done is basically up here, I'm giving you an example of the type of response that you should have when you are describing the relationships here. So just an example, the cost of a package of light bulbs and the number of light bulbs in the package has a correlation coefficient value near 1. Okay, so you're going to want to include that. This means that these variables have a very strong positive relationship. Okay, so is it a very strong positive relationship that the variables have? That's something you're going to want to put in your responses for 8.3. In other words, the price of the package is very closely related to the number of light bulbs in the package. Okay, so very closely related. Okay, that's going to be a strong positive relationship. And when one of the variables goes up, the other variable tends to go up too. Okay, and that's going to go be a positive relationship. So that's the kind of response that you're going to want to have for these down here. So for the correlation zoo, for each situation, describe the relationship between the variables based on the correlation coefficient. Make sure to mention whether there is a strong relationship or not, as well as whether it is a positive relationship or negative relationship. Okay, and that's basically just what I went over. So number one, number of steps taken per day, and the number of kilometers walked per day. Okay, instead of reading all these out, what I'm going to do is I'm going to put the answers in, and then I'll come back and just discuss them really quickly. So for number one, there is a strong positive relationship. An increase in the number of kilometers walked tends to go along with an increase in the number of steps taken per day. Okay, so that one is pretty much common sense. Okay, so the correlation coefficient is positive. It's pretty high, and that just means like if you walk more distance, you're going to take more steps. Number two, temperature of a rubber band and the distance the rubber band can stretch. Okay, so we're looking at the temperature and how far it can stretch is 0.84. So there's a strong positive relationship here. So what that means is an increase in temperature tends to go along with an increase in the distance a rubber band can stretch. So if you stretch that rubber band, okay, you are introducing a force, and so that is going to increase the temperature, and that also increases the distance a rubber band can stretch. So if that rubber band is hotter, okay, it's going to be able to stretch further. I think that's what I was trying to say. Okay, all right. Number three, car weight and the distance traveled. Okay, so if the car weighs a lot, okay, it is not going to be able to travel as far on a full tank of gas. Okay, so the relationship is negative, but it's pretty strong. Okay, the next one, average fat intake per citizen of a country and the average cancer rate of a country. Okay, so we might think that that's going to be a really strong relationship, but when we look at the correlation coefficient, we see that it's 0.73. Okay, so it is a moderate positive relationship here. For number five, score on a science exam and number of words written on the essay question. Okay, there's a weak positive relationship. So an increase in the number of words written on the essay questions tends to go along with an increase on the score for a science exam. But the relationship is weak. So let's say you write a whole bunch of words, but you don't understand the concept, or maybe you understand the concept and write a lot of words, but multiple choice and those types of problems are, you answer them wrong. Okay, so there is a weak positive relationship. So there is a relationship, it's just weak. And the next one, there is a negative relationship. Average time spent listening to music per day and the average time spent watching TV. So you would think that if you listen to more music, okay, the amount of time that you have to watch TV is going to be less. Okay, so there's a weak negative relationship. And so this is going to be the explanation for why that is. All right, the next one. Are you ready for more? A biologist is trying to determine if a group of dolphins is a new species of dolphin or if it's a new group of individuals with the same species of dolphin. The biologist measures the width in millimeters of the largest part of the skull, zygomatic width, and the length in millimeters of the snout, rostral length, of 10 dolphins from the same group of individuals. The data appears to be linear, and the equation of the line of best fit is y equals 0.201 x plus 110.806, and the r value is 0.21. Okay, so here's all our data. We can see here that the r value is not very strong. Okay, we see that our slope is going to be a positive, and our y-intercept is 110.806. So let's take a look at this problem. After checking the data, the biologist realizes that the first zygomatic width listed as 147 millimeters is an error. It is supposed to be 180 millimeters. Use technology to find the equation of a line of best fit and the correlation coefficient for the corrected data. What is the equation of the line of best fit? and the correlation coefficient. Okay, so up here we see that this information, okay, the first one is incorrect. Instead of 147, it should be 180. Okay, so let's go ahead and put this information, this data into Desmos and get the new line of best fit. Okay, so I have entered in the data, the original data, and I have also done the line of best fit estimate. Down here, we can see that we have our slope, our y-intercept, and then we can see that our correlation coefficient is 0.2012. Okay, and so that's where we're getting our line of best fit for the information with the incorrect data. Now, what we're going to do is we're going to switch this to 180. Okay, and then we see the new parameters, okay, the new information. Now, when I was putting this information in and I did the line, I came up with this, okay, I was like, where's the line? Okay, well, you're going to have to zoom out. Okay, now where's that data? Oh, there it is. Okay, so we're going to come up here and we're going to look at that information right here. Okay, let's go back and put this as 147. Okay, and we can see it looks totally different, right? That information looks a lot different when we have the outlier. Okay, and so let's go back here and put this back in. So this is going to be 180. Okay, and then we've got, whoops, what did I do wrong? Oh, there we go. And here's our new information. So let's go ahead and just write that down on our information here. Let's see, let me go back. Just make sure that I have everything right. Okay, good. All right, so we pulled this back over. Okay, so down here, let's go ahead and write our new equation. Y is equal to 0.693x, okay, minus 18.373. Okay, and we have an r is equal to 0.76. Okay, so that is the line of best fit and the correlation coefficient. Compare the new equation of the line of best fit with the original. What impact did changing one data point have on the slope, y-intercept, and correlation coefficient on the line of best fit? Okay, so here the slope increased and the correlation coefficient got closer to 1. The y-intercept also changes significantly. All right, so I'm going to go ahead and put that down for you so you can copy it. And so why do you think that weak positive association became a moderately strong association? And explain your reasoning. So let's just go back really quick and take a look at the graph here. Okay, so right now this is, oh, let me get rid of this one if I can. Over here we have the point that we're looking at. Okay, so 288 and 147. That's this point right here. Okay, and so what they're saying is, let's go ahead and change this to 188. Okay, so before we do that, come down here, take a look at our correlation coefficient of 0.2. Okay, now when we change this data point and we make it 188? Sorry, 180. Okay, so we'll make it 180. Okay, And so now 288 and 180. Okay, so which point is that? 288, 180. Okay, so this point right here. Okay, so it moved up significantly. All right, and so now we can see that it is closer to going through that line of best fit. We say that our correlation coefficient down here, the R is 0.756, and yeah, so that's going to show us basically what happens when we change that data point. Oh, and look at my cow, isn't he cute? Okay, um, let's look at the next one. Use technology to change the y value for the first and second entries. How does changing each point's y value impact the correlation coefficient? Okay, so changing the points to numbers well above or below the existing linear trend in the data makes the correlation coefficient get closer to 0. Okay, so not correlated. Okay, so we can change that, those data points. Oh, my cat was so cute. Let's see, where is it? Okay. So if we change this to like 100, let's do 190. Okay, so we'll do 190. How about the next one? We can do to like 259. Oh, let's not do that one. Let's do 200. Okay, so not that. We don't want it to flip all the way around. Why is it doing that? 247, 200, 197, 196. Okay, so we can see that it's totally changing, right? Those values when we alter those data points. Okay, 190. Let's see, 99. Let's do 100. Let's do 50. Okay, so it's changing those values. What else can we do? Okay, yeah. So can you change the two values to get the correlation coefficient closer to 1? Okay, so you can get the R value closer by changing the two values that appear furthest from the line of best fit. Okay, so I put these numbers in for you. You can go ahead and just play with the values to see how that works. And also down here, you can work on C. Okay, and I did put the answers down here for you. Okay, another thing. So when I was changing these values here, and I went up to like, let's see, 200. Okay, why does it do that? Okay, why did it totally flip the line here? Okay, right here, let's do 100. Okay, and now, why did it change that? Okay, slope. That's what I want you to kind of play around with a little bit. Okay, so let's take a look here. Okay, if we put it to 100, okay, so just play around with those values and see if you can explain why this is going to change so much. Okay, why does that happen? So if we put 120 here and we put 120 here, do you see what happens? That line gets closer to being in the middle of these, okay, and that's kind of what makes sense. Here we have 0.14, so it is getting closer to 0. So again, play with these values, see what happens with the correlation coefficient, and in the end, just see if you can understand exactly what's going on. And as always, okay, what I want you to do, oh, my cow is so cute, is to go and read the summary. Okay, the summary is pretty good. So just read through that and see if you can make sense of everything in the lesson and how it's all wrapped up here into our summary. Okay. All right. That's it for lesson 8.